Okay, mag-record na ko ha. So, okay, good morning. So, our topic for today is all about the unit load method or the virtual work method. And in this meeting, we will focus on its application to determine the deflections for beams. Okay? So, we will start. Okay? Dali lang mga kapatid. Okay. So, just an overview for the unit load method. What is emphasized here is that the work done by all the external forces acting on our structure is transformed into the total internal work. So it can be seen by this equation. That is what it simply means. Meaning to say that if we apply external forces, all those the total work could be transformed into it is also equal to the total internal work. So it is as simple as this equation. Okay, you have your external work is equal to the internal work. Okay, so that's it. So it can be illustrated by this figure here. Meaning if you have an applied force P and that force P causes a total elongation of delta, then the work done is equals to P times delta, as can be seen by this equation. And the total external work is simply equal to the total internal work. Now, if you also apply moments, say for example, you have a moment M, and it causes rotation theta, then the work done is simply equal to this equation, the moment times the total angle of rotation. Okay, so for beams and frames, the displacement or the rotation is defined from this figure. So if you have a total, if you have a simply supported beam with uniform loads, W, then at point A, it may cause your beam to deflect at point A equal to delta, and it may have this corresponding rotation. Kini. Now, simply put, in equation form, if you wanted to determine the vertical displacement at point A, then you will simply need to use this equation as derived from the virtual work method of the unit load method. So, as you can see in this component, you are going to apply a virtual load, 1 unit load, times delta is simply equal to the integral of the small letter m. These are the moments due to your internal, due to your virtual load, and the big letter M stands for the moment caused by your actual loads. So you simply evaluate this equation here. So you simply integrate this expression. So simply put, para wanilabad. Now, if you also wanted to determine the rotation at point A, again, you will apply a unit a couple moment at point A. And the corresponding rotation is simply equal to this expression here. If you notice, these two expressions are just very similar. So we have here your delta, and we have here our theta, since we wanted to determine a rotation. And as you can see, guys, the expressions are very similar. M is the moment due to your unit load, and M is the moment due to your actual load. And you simply evaluate the expression as expressed in this formula here. So it is simply equal to mm over EI, the integral of mm over EI. So similar lang siya. Anyway, we will go directly to the application. Now, the procedure for analysis would be one, you need to set up your virtual moments. And to do that, we place a unit load at the point where we would like to determine you place a unit load at the point where we would like our vertical deflection. If you wanted to determine the vertical deflection, then at that particular point, we will also apply a unit load. If we wanted to determine the rotation, then at particular point, we will apply the unit load for unit moment. Now, but then second part is we also need to set up our real moments M. So we are going to create expression for moments at different sections of our beam. Now, once you have set up the virtual moments, the equations for virtual moments and the equations for real moments, then that's the time that you will use the virtual work expression, the virtual work equation. Okay, to determine the displacement or the rotation. So that's it. Now we will have our illustrative example such that we can apply what was discussed recently. Now, in this case, we have here a cantilever beam with fixed support at point A, and it is uniformly loaded with 12 kilonewton per meter over a distance of 3 meters. And we wanted to determine the displacement at point B of our steel beam. And in this case, we just take AI as constant. So what will happen? So one is you need to set up your virtual moment M. And with that, since we wanted to determine the displacement at point B, the vertical displacement, then we will apply a unit load at point B. Since in this case, we have turn off sa sakuan mic guys para wa kayo interference. So if we are going to draw our elastic curve, then most likely the deflection will be downward. So we will also apply the unit load acting downward. And from this, we need to set up our equation for virtual moment. Now, so we can set up any origin, either from A or from B. In this case, it would be a lot easier if we are going to recon from point B. So, now na itong equation. We need to set up this expression. And from this, we can see that the moment is simply equal to -1 times x. Negative simply because in our convention, once ang top na to will be under tension, then we would consider that as negative moment. And if our bottom fiber is under tension, then that will be, this is negative and this is positive. Okay, so as you can see here, it is clearly this moment, this causes negative moment, and it is simply equal to 1 times x. Okay, so okay na. Question naman.
Ang 1 kilonewton, sir, gi-assume lang na siya, sir.
Yes. No, one ra gyud siya atong i-load simply because mag-apply tag unit load. Pagkos na, oo, kay if we wanted to determine the vertical deflection, then we will apply a 1 unit load. So in this case, since our unit is expressed in terms of kilonewton per meter, then the unit load would be equal to 1 kilonewton. Are we clear?
Yes, sir, yes.
Okay. So if our unit would be 1 pound per foot, then we can also use the unit load of 1 pound. Okay na? Okay.
Thank you, sir.
Next, we will set up a real moment. Now, a real moment is simply equal to kini. Since we have 12, again, the moment will cause, in our sign convention, it will be negative moment. So, what will happen here? If we are going to cut from this section here, if you will pass a cutting section, then the moment will be equal to, we have 12 times x, which is represented by this. This is equals to 12x times the moment arm of, if this is equal to x, then this must be equals to x over 2. Nakita naman nyo na. And with that, it is very clear that the moment is simply equals to x over 2 times negative x over 2 times 12x, which is simply equal to a negative 6x squared.
6x squared.
Okay. Okay. So, wala may mga discontinuities, then we can take up this virtual moment equation, isa lang ka-setapan, and the real moment equation. Okay? So, we already have our m, small letter m, and we already have our moments for big letter m. And with that, we can now use the formula, which is equals to 1 times delta is simply equal to the deflection at B is simply equal to, evaluated from 0 to L, equal to m dx over EI.
EI.
Okay. So, which is equal to, what is the total length? 0 to, starting here, 0 to 3. So that will be our limit. And a small letter m is simply equal to negative 1 times x. And this m here is equal to
6x squared.
negative 6x squared dx. Oops. Over
200
EI.
times
Ay na lang sana.
EI,
Kay
sir.
katunggaan ako sa previously na ako lang i-take EI equals to constant. Okay? Kaya para madali lang sa ta. Okay? So anyway.
Sir.
So with this, evaluating this expression, then we can get, we have 121.5 over EI. Okay. Now, take note that we have a positive result. And the direction of our unit load applied is downwards, which simply means that we have the right, we assume that our deflection will be downward. And since this is positive, then we have a downward deflection also.
Sir, kibali sir og negative.
Then it will be opposite.
So nasa sa
pasaka siya. It will be upwards. Yes.
Okay.
Okay?
Mag-change lang ang iyang sign kibali sir.
Ma-change. Opposite sa imong gi-assume.
Okay.
Okay? So that's it. Now we will have another illustrative example. Now this time we are going to use values for our EI. Okay? Next. Okay, this one. So we are going to determine the deflection at point D. using the virtual work or the unit load method. Now, if you notice, guys, for this particular beam, we have a simply supported beam with a concentrated load at point C.
C. Point
And
C.
the magnitude is 150 kilonewtons. Now, we have a problem here simply because there we have different moment of inertia. We have different segments from A to B, and B and D, E. The moment of inertia is this. We have 300 times 10 to the power of 6 quartic millimeter. On the other hand, for sections B to D, we have twice the moment of inertia of AB and DE. Okay? Now,
Yes, sir.
with that, we can say that our I for segment BC and CD is equals to 2I. And our moment of inertia for DE and AB is equal to I. Are we clear with that? So
Yes, sir.
what we are going to do next? So since we are required to determine the vertical deflection at point D, we will set up the virtual moments
Vertical
and the
moment.
actual
Real moment.
real
Actual moment.
moments. Okay. So how do we do that? Take note, you are going to apply your virtual load at point D. In this case, we wanted to determine the vertical deflection, then we need to set up this illustration here. Okay? Now take note, guys, that we have discontinuities for A, B, B, C, C, D. No? It could be nga maglahi-lahi. They would have different setup for moments. So what we're going to do is we are going to create segments. In this case, such that it would be safe, we are going to create 4 segments: AB, BC, CD, and DE. Okay? So probably I can create here this, we have segment, oops, and magaglain man. Let me have, ako sa ni-erase. Whoops. Okay, so we may have 4 segments AB, and we have BC, then we have CD, and we have ED. Then probably we can set up different origins. So, and we can have our another for our limits, which is in meters. Then we can have our expression for our EI. Then we can have our expression for our virtual moment and expression
Real
for
moment.
our real moment. So for segment AB, we may select our origin starting from A, and for segment BC, we can select our origin to be at A, and for segment CD, we can select our origin at A, while at segment DE, we may select our origin to be from E. Okay, now the limits would be, in this case, for segment EB, it would be from 0 to 3. And for segment BC, since our origin is from A, our limits would be from 3 to 6. And okay, since we have that, and from C to D, our limits would be from 6
6 to 9.
to 9, as you can see here. 0 to 3, 3 to 6, 6 to 9. Okay? And for segment DE, and if our origin is from E, then our limit would be from 0 to 3. No? 0 from starting here to here, our limit would be 0 to 3. And for EI, as we have noted earlier, for segment EB, we only have EI here since we have this
Constant.
expression. Kana. Diba?
Ay, din. Oo,
Okay.
sir, 300.
So we have I only for AB and DA, whereas for B, C, and CD, we have 2I. So what will happen here? For segment BC, we have 2 EI. For segment CD, we have 2 EI. And for segment ED, we only have EI. Now, how about for our moment? Now, for our moment, we can see that if you are going to apply a unit load at D, acting downwards, then the reaction here would be equal to 1/4. And the reaction here will be equal to 3/4. Diba? Na naman na siya. Okay? So, the total length is equal to, pila? The total length is equal to 12 meters. So,
12.
we have 3 divided by 12. No? It is simply
4.
equal to 1/4. 1 minus 1/4 is equals to 3/4. So we have these reactions here. Okay. So anyway, if you are going to use the equation, moment equation, solving for use a moment about point A or for point E, ako naman na siya shortcut. Para dali. Maura maghihapong gawas. Okay. So our M here, since this causes positive moment, our M here would be, we have 1/4 times X, or simply equal to X over 4.
4.
Okay. Likewise, from B to C, no, this will be now our X. So we have, again, 1/4 times X is equals to X over 4. And 4. For C, segment C to D, again, we have 1/4 times X, or X over 4. However, our moment expression, small letter m, for segment DE would be equal to
3x over 4.
Yes, 3x. No. Oh, yes, that's it. 3/4 of x. Okay. Now, how about for our moment? So if you apply for our real moment, our actual load is 150 kilonewton. Divided by 2, because naman na siya tunga at midspan, that our reactions would be this, 75. Then if you are going to write the expression, this is our M and this is our M. So the moment would be equal to 75x for segment EB. The same is true for segment BC.
T.
Okay? So guys, 10 minutes
sir.
na lang guys. Paspasan ko ni. Ay, anyway. So we have 75x.
75x na lang.
Okay, however, for segment CD, take note that we can now see this force here, 150 kilonewton. So what will happen? So we have the moment would be equal to 75 times x. The moment would be 75x minus 150 times, what is this distance here? This distance is simply equals to,
1.5.
this is 6, and this is
Ay,
total distance
6.
x. This
3.
will be equal to, this distance equals to x minus 6. Right?
Yes, sir.
Okay. And
Ay,
on the other hand, the moment for DE and our origin is from E, then we have here 75x. Once you have done that, then you can easily evaluate the expression 1 delta is equals to the integral of mm
over EI dx.
okay. And take note, guys, we have different segments AB, BC, CD, and ED. Okay, so ato siya ilahi-lahi. So we have 1 times delta is simply equal to
0 to 3.
okay. So EI is constant. We can take EI out. So to simplify, it is simply equal to the integral of, for
0 to
segment EB,
3.
0 to 3, and the expression is simply equal to x
X over 4
over 4
times
times
75x
75x
dx.
dx. Okay? Plus, di na ako isulat. Kuha na. Sige na lang, dire na lang. Plus, the limits would be
Integral
3
3 to
to
6.
6. It is simply equal to
X over 4. Na may 2, sir. 2EI man.
i-over mo. So, pwede na ito ipagawas anyway. So, we have x over 4, 75x
5x
dx. And since we have over man siya 2, then pwede na ito ipagawas ang
1/2.
1/2. Plus for segment CD, we have, again,
6 to 9.
we have 1/2 because our EI is 2. We have, okay. And evaluated, our limits would be 6 to 9. Evaluated, our moment M is x over 4 times
75
minus 150x. If you are going to simplify this expression, this becomes
negative 75
negative 75x plus
x
900
minus sir.
times dx. Plus the component for segment ED, evaluated from 0 to 3. 0 to 3. And we have 3/4 x times 75 x. Oh, I forgot the x here.
Walang
dx. Okay?
sir.
So, evaluating this expression, this becomes 1 delta is simply equal to 2,193.75 over EI. And we have 1 times delta is simply equals to 2,193.75 over, we have 200. What was our value? Okay, E is 200 and our I is 300. 300. Now, this becomes 0.0366 meters or equal to our delta D. I forgot. This is for D. D is simply equal to, we have 36.6 times 1,000, 36.6 millimeter. In this case, since this is positive, this acts downward. Okay, so that's it.
So, tama, sir.
Hmm? So,
Sir, excuse me.
what? Ano man?
Pwede mo.
Oh, sige, sige. Ano
Kanang
man?
dit sa segment CD, sir. Di ba
Sig-
na po EI, sir? Di ba 2 EI ba na, sir?
Oh,
Sa una
nakiri
na
na.
lang,
Nakiri naman to
pwede
na
ra
to.
po.
Nakiri naman to.
Okay.
Kaya ipagawas ng kinikining expression 1/2. Kaya ana man na siyang expression ana 1 over EI. Sa segment CD, we have 1 over 2 EI. Ipagawas naman to natong EI daan. So natay kini nga component 1/2 kana, which is this. This is for segment CD. Sa CD man nga part, kini this is for segment BC, and this is for segment EB, and yan. This is for segment kini, this part here is for segment ED. Kita nimo? 1 over 2 man na siya. Kaya ito ipagawas. Gets nimo? Ibali, ang nahita ba ng expression, you have, this is the original expression, mm over 2 EI dx. So it becomes, ato ipagawas, since this is constant, we have 1/2 integral of mm over e. Pagawasan po na to itong EI previously. dx, kini na lang yung makita. Kini. Kana.
Oo, sir. Okay, sir. Thank you, sir.
So what else? So since we're running out of time, maybe tama lang sa ako diri. Okay, kay 2 minutes na lang ang nabilin. So do you have any more questions? Anyway, what is important here is we have shown the different techniques utilized here using different segments. Then ang sa mga limits o ang pag-evaluate sa ato ang EI in our integrals. Okay? So nasabtan? I hope medyo naklaro.
Yes, sir.
Naklarex ba, guys?
Oo, sir.
So, are there any more questions? Sige, kaya ito i-address. Take
Kuan, sir,
advantage unsa man.
kaning downward, di ba, ning 1 kn, sir? Nganong
Yes.
sa kaning sa gamay na m, sir, wala siya na negative?
Asa? Positive man ang ato ang moment. Kini.
Okay.
Like for this example here. 75 times x. Kini nga moment, take note nga, again, di na to limtan. Basta ingon ana gani, positive na. Basta gani
Ay,
ana ang
tama.
bending, kana siya, negative na siya. In this case, dari po kaspikas, ngari ka ni Agi, origin sa E. Take note nga, ang bending niya, paani, kini man siya. So positive siya, right?
Oo.
Kanira ang bantay. Okay?
Okay.
Are we clear?
Sir. Yes,
What
sir.
else? Clear na? So we have time remaining 1 minute. Limited naman ni siya kang sa Zoom, 40 minutes naman good. So I hope you learned something. Okay, guys?
Thank you kayo, sir. Oo, sir.
Okay, so thank you also for participating, and if I were you, you practice because you will only learn once you do it yourself. Okay? It's quite different if nagtanaw lang ka, and it's quite different if you are doing it yourself. Okay? You try it. Probably you can practice maybe similar to this, or you can repeat this and probably do the process. Then you will try different the other different beams or different loadings, different combinations. It could be uniform load. It could be simply supported, or it could be there will be an overhang para jud nga you will try to anticipate different setups. Okay? Are we clear? So that's it. So that's all for this meeting. Bye-bye and thank you. By the way,